Today we will see that how the instantaneous description of Turing machine is carried out. So what is the ID, how we are going to represent the principle of Turing machine, what is the ID behind it. Okay, we will learn how to describe it. Fine. So what a Turing machine does, we have learned in our previous lecture that it will process a infinitely long tape, right? So it we have seen that whatever the string we are going to process, it will have that in its tape, and before the starting of that string there will be infinite number of blank positions in the tape, and in the right there will be infinite number of blank positions. So any finite number of moves, and the TM can have visited only finite number of cells. So even though the number of cells visited can eventually grow beyond any finite limit. So as we know that since the Turing machine is capable of implementing any kind of algorithm what a computer can process, so there may be certain situations where this finite number of moves which we are saying may go up to infinite, right? It may process infinite number of symbols. So thus in every ID there is infinite prefix and infinite suffix of cells that have never been visited. So it intentionally we have to keep the tape in such a manner that whenever this processing goes beyond finite limit, that when it is processing infinite number of symbols, so space should be there in the tape only, right? So we should keep the cells ready. That's why that those cells are initiated with blanks, and it is kept with the tape from beforehand. Fine. So these cells must hold either blanks or one of the finite number of input symbols. So it may have blank, it may have any one of the finite symbols, nothing that we are just initializing the tape symbols in that fashion to mark that okay, we have the cells with us. We just show in an ID only the cells between the leftmost and the rightmost non-blanks, right? So whatever the cells we are going to process are those cells which are between the leftmost and rightmost non-blanks. Those cells we are going to process here. Now, under special conditions, when the head is scanning one of the leading or trailing blanks, a finite number of blanks to the left or right of the non-blank portion of the tape must also be included in the ID. So this is a special condition whenever the head is scanning one of the leading or trailing blanks, so it means it has reached any of the blank position, so a finite number of blanks to the left or right of the non-blank portion of the tape must also be included in the ID. So since it has gone to the cell where a blank is present, we must incorporate those cells into the ID only, otherwise we are not going to keep those in our instantaneous description. Fine. So in addition to representing the tape, we must represent the finite control and the tape head position, right? So in our ID, so we should not be limited to keep the what are the positions or what are the processing symbols in the tape only. We also have to keep the position or location of the finite control, means which area of tape symbol or which cell of tape symbol my Turing machine is scanning now. We need to specifically mention that as well, right? And the tape head position, right? So where the finite control is now and which symbol it is processing, where the tape head is now, that all those things we have to mention there as well. So if this is a situation, we have to embed the state in the tape and place it immediately to the left of the cell scanned. So in this fashion we have to represent ID that wherever the whichever the symbol it is scanning, right, so we will place the state, means the present state where the Turing machine is processing now, and the area of cell or the cell which input symbol it is scanning, we should keep it together to represent the ID. So to maintain the situation correctly, it is quite easy to understand that we should not use the same kind of symbol to represent the input string as well as the state. Means if say we are using the input string like this x1 x2 x3 x4, and if again we use this x1 x2 as to mention the or to depict the different states of the Turing machine, then we will get confused. So if we have to keep in mind, we cannot use the same type of symbol to represent both the tape symbols and the states. Definitely we are going to use q1 q2 q0, right? So in this fashion we are going to represent the states, and for the input symbol or the tape symbol we will use x1 x2 and x3. So we should keep in mind that we should not use the same kind of symbol, otherwise it will be a confusing situation, right? So we have to keep all those things in mind. So let us see this one, that say we are having a string x1 up to xn, right? So it is the total string which we are going to process, and it is the area between the leftmost blanks and the rightmost blanks, right? And this we are going to process. Now see here, when this q is scanning the ith symbol from the left, you can see we have written x1 x2 up to xi minus 1, then q, then xi, then xi plus 1 up to xn. So just see whichever symbol my Turing machine is scanning right now, we will put the state in which it is processing now just before that symbol scanned, right? So this is the fashion we will use to depict which symbol or where the location of the tape head is right now, where the finite control is positioning right now, and we will depict it in this manner. Fine. Now let us see it formally. See, we are having a Turing machine M, and this is a tuple notation. We know what each symbol means. Now here again we are use that tungsten symbol that we have used in PDA to see that to represent the transition. We know how to use the tungsten symbol. Just see the tungsten symbol, there will be a star above and M below it. Here we are using M intentionally, we have not used in the case of PDA. Here M means this is a feature of, or we are using this tungsten symbol to represent the transition in case of a Turing machine, right? So here we may keep the M with it, we may not keep, and tungsten symbol and a star above it means there may be 0 number of moves, there may be 1 moves, and maybe more than 1 number of moves, right? Now see, suppose we are having a transition, say delta of q comma xi, it is changing to p comma y comma l. So we have learnt in our first lecture what is the meaning of it. So whenever my Turing machine is at state q and it is scanning any symbol, say q xi, so it will transit to next state named p. Here it will write y there, y will be written at that location, and it will move to the left. So if we are having this symbol that x1 x2, just see here we should place q just before the xi, right? And after changing it, what will happen, you can see that this because the movement is leftward, it will move left. So what p is where p will lie, you just see that the position of xi, right, we had qxi here in between, just see the position of xi has been changed to y, right? So and since it has to move leftward, so now the position of p will be one place before where the q was, so that will be just before xi minus 1. So what will be the changed state or the changed representation? It will be x1 x2 up to xi minus 2, then p will be there, then xi minus 1, then at the place of xi, y has been written, or xi has been replaced with y, and rest will follow as it is, right? So this is the way which we are going to represent the transitions. Okay, now if there are some special situations that how this move reflects the change to state P and the fact that the tape head is now positioned at cell I minus 1. So there will be two important exceptions. What are those exceptions? Let us say if I equals to 1. Right, so if I equals to 1, then M will do what? M moves to the blank to the left of x1. Right, so x I equals to 1 means x1, so it will have nothing to the left, right? So what will happen, just see, q then x1 x2 up to xn, so it will change to that, it will go to p, right? And this x1 will be replaced with y, and p has gone before b, because there is no more symbols left in there remains in the left of it where p can move. So the before x1 there is nothing but blank, so this situation may occur. Right, now if I equals to n and y equals to b, right, so what will happen, just see, so q is scanning x, means your I equals to n, so it is scanning xn. So see, q is before xn, right? So after that what will happen, so since it is when y equals to blank, then what will happen, p will just be at the position of q, right? It will it is not going to change anything, right? It means it is a blank only, so it will get merged with it. So p will get merged at that place. Just see, it is there, and this has happened, right? So it is not going to move to the end since y is equals to blank. So these are the two special situations. Now let us see if instead of left the movement is right. So I think it is very easy to understand from the first description, generalized description. So what it is going to do, since it will move right, just see, now the position of p previously was at this position before xi, since it is scanning the ith location. So after moving right, p will move where, p will move just after this xi, which has been written to y now. So after y, p will be placed. And similarly, if these two are exceptional cases, and you may refer to the previous slide to understand, the thing is same. Instead of moving left, it is going to move right, nothing else. The situations will be similar. Now let us see an example. Say we are given one one language, and we are going to construct a Turing machine which is going to accept this language, say 0 to the power n followed by 1 to the power n, where n is greater than equals to 1. So that means at least 1 0 and at least 1 1 should be there in the string, right? So how it is going to do, or how it is going to work? Initially, it is given a finite sequence of zeros and ones on the tape, preceded and followed by infinite number of blanks. So this is the way of our initiation, or this is the approach in which we begin to construct a Turing machine. We will have all the finite set of zeros and ones in the tape. We have to check whether the finite set of zeros and ones are same or not, or equal or not, right? If they are equal, then my Turing machine is going to accept this string, otherwise it is going to reject the string, right? So there will be finite number of zeros and ones, and that total finite string will be preceded by number of blanks, infinite number of blanks, and will be followed by infinite number of blanks, right? And alternatively, the TM, what can be another approach which we are going to follow throughout this lecture, that TM will do what? It will change 0 to an x and then 1 to a y until all zeros and ones have been matched. So this is an easy approach, since you can see that what is the basic description of a Turing machine. Whenever it is at one state and it is scanning one symbol, it will move to another state and change that position to with another thing, and will move either left or right. So this is the fashion. So our approach should be like this: whenever it is encountering a 0, it will change it to another variable, so that we can keep the track how many zeros we have encountered till now. And whenever it will encounter any 1, it will change it to another variable, so we can keep the match then only, right? So let us see how it is going to change. Now in more details, if we have to explain this one, starting at the left end of the input, it enters a loop in which it changes a 0 to an x and moves to the right over whatever zeros and y's it sees until it comes to a 1. What is the meaning of it? Say whenever it is finding a 0, I think the concept will be clearer when we will in the next slides we are going to represent this using a transition table. You can see there that how the situation is working. So what it is doing, it will enter a loop, means whenever it will encounter 0, it will keep on changing it to an x, right? So whenever it is changing to an x, it is moving to right and just sees what the zeros are there, so it will keep track of zeros and also keep on visiting y. Why it is keep on visiting y? Because in this situation my ones has been converted to y, so I'm not going to convert ones to y here. So until it encounters a new one, it will keep on scanning it, right? So it changes the 1 to a y and moves to left over 0. So means whatever it is doing, so in one state it is going to convert the zeros to x, in another state it is going to convert the ones to y. In between this two means changing of zeros to x and ones to y, there should be a transition for which it should move from the initial state to that state where it will change the ones to y. So in this situation what it will do, so in this situation with 0 value it will move to the next state and keep on visiting zeros and y's, and now if it finds any one in the next state, it will going to change those 1 to y's, and again if it finds zeros there, what it will do, if it finds any 0, it will change it to x and keep on repeating it, right? So if this is non-blank input is not 0 followed by 1, means if the situation is like this, all the zeros has been converted to x and all the ones has been converted to y, that means it is having same number of zeros and ones, so it will accept, otherwise it will not. Okay, now let us see it in the form of in this transition table, and in the later slides we are going to explain each and every transitions identically. So for the beginning, just see what are the states we are going to incorporate here. It is x0, x1, x2, x3, x4. Input symbols are my 0 and 1. These are the tape symbols scanned, and delta is my transition function. Initial state is q0, b is the blank symbol, q4 is my accepting state or final state. Okay, so this is the total transition diagram which will be explained one by one in the later slides. Now, as M performs its computation, the portion of the tape where M's tape head has visited will always be a sequence of the symbol described by the regular expression x followed by 0 followed by y followed by 1 y, right? Because there may be some zeros which has been converted to x already, there may be some zeros which has not yet been converted, there may be some ones which has already been converted to y, and there may be some ones which are yet to be converted. So this is a situation, right? Now let us see how this transition table has been built. Okay, initially we are at state q0. Fine, you can follow the table given to the right, and if you find it hazy, you may consult the study material, or you may see the slide where the picture is much clear. Okay, now this initial state is q0, and M also enters the state q0 every time it returns to the leftmost remaining 0, right? So what it is doing, see, for 0, it is doing what? Whenever it is seeing a 0, it will change that 0 to x. It will do a transition, that is, it will move to next state q1, and it is moving to the right, right? Means first the zeros it is going to encounter, and it will direct the Turing machine. Okay, now keep on moving right and keep on scanning the symbols, so the movement should be right, and the change should be from 0 to x, and there should be a transition obviously. Now if m is in state q0 and scanning a 0, the rule in the upper means left corner of the this table is to go to the state q1 and change a 0 to an x and then move right. So I told you this one, right? Next, now it is in say state q1. Fine. So m keeps moving right over all zeros and y's. Now see the here you may find it quite interesting. Okay, so it has not changed all the zeros to x, so why it has come to this new state? Because whenever a change is being done, if we are going to stay in the same state only, we will never finish off, right? We have to do a transition. Now in this state it is not going to change any zeros now, right? So what it is going to do, if it finds any 0 here, just see at q1 if it gets a 0, it is not going to replace it, because the job of this q1 state is to replace 1 with y and not 0 with x, because we are dedicatedly mentioning two different states where one state's responsibility is to change zeros to x and other state responsibility is to change 1 to y, right? So whenever it will get 0, we will later on change it to x, fine, no issue, but now it will keep on scanning, and whenever and it will keep on scanning y, but whenever it will get a 1, it will do what? It will keep changing it to y, and see now the movement will be at the left. Just see the second block of this q1 row. So in case of q0, where 0 is been scanned, it will replace to x and will move to right, but whenever at q1 it will encounter any 1, it will convert it to y and will keep on moving to left, because it has to come back to the means need to scan the left symbols whether any more zeros are there or not, right? But if m sees an x or a b, it dies there. Why? Because if it finds any x there, that means what? That means it has been visited beforehand, right? It has been converted to x. That means there are more number of ones, it has not been converted to y, right? So it has to be die, otherwise the result will be unequal number of zeros and ones. So there may be zeros which has not been visited, but there should not be any zeros in between those one where it has been converted, so it should die there, and blank will not be there as well. Okay, now instead q2, fine, so it has moved to q2 now. Instead q2, m moves left over zeros and y's remaining in state q2. So whatever the remaining part are there, so it will keep on moving over it, right? See, it has been mentioned in the table. Now when m reaches the rightmost x, which marks the right end of the block of zeros and that have already been changed to x, m returns to q0 and moves right. Right, so whenever this rightmost x has been visited, so it is going to do what? Again it will come back to the original position, right, and keep on moving to the right. It has also been depicted in the this table. Now there may be two cases. Now after this move, if now m sees a 0, then what will happen? So more zeros are left, again it will keep on doing the same process whatever we have described so far. Now if the situation is a different thing, that if now m sees a y, then it has changed all the zeros to x, right? Now if all the ones have been changed to y's and the input was of the form 0 to the power n and 1 to the power n, m should have accept. Thus m will do what? M enters the state q3 and starts moving right over y's, right? If the first symbol other than a y that m sees is a blank, then indeed there were an equal number of zeros and ones, right? So m enters the state q4 and accepts. So after scanning everything, all the zeros and ones, what will remain? Blank, right? So if it encounters a blank, it has to go to the final state, that is q4. If not, if encounters another one, then there are too many ones. So since it has reached the end line, so there should not be left out anything. So we have already matched the number of zeros and ones. So if any more 1 or 0 comes at this situation, it will die, right? So see, it will at the q3 state, if this two situation occurs, only for y and b, that is going to move to q4, and for other inputs it will die. It has no transition shown, only dashed are there, so that means it will die over there. Okay, now let us see one string which it is processing. Let us see it is going to process the 0011, and this string should be accepted one, right? Because equal number of zeros followed by equal number of ones. And if you follow the table, the same table, and this will be the path which has been depicted just at the bottommost position of the slide. That is, first it will have q0, the input string it is going to process is 0011. So on encountering a 0, what it is going to do, see, it is replacing the first 0 with x and is moving to q1. Again, at q1, if it sees a 0, what it will do, it will keep the 0 and will move to right. Now if it sees 1 there, what it is going to do, it will keep on moving, right? It will be on at q1, and it will do what, it will move to the left, and just see the position of q2 is now just before the 0, and it has changed the 1 to y. So in this fashion, if you keep on moving, you will see at the end all the zeros has been converted to x, that is xx, and this 1 has been converted to y, that is yy. So xx, yy, and now a blank has been scanned and q4 has been reached. So there will be blank after q4. So it has got accepted. Fine. Now let us see for another string, that is 0010, right? So 0010 is a string which this machine is not going to accept. So following the same fashion, you will see at the end it will come to this situation, xxy0. Now see, 10 has not been changed, right? And it has stuck to q1 state only, so it has not reached to q4 state, which is our accepting state. So this string will automatically gets rejected by the Turing machine. So you may follow this one, just the steps has been written here. I think it is not worthy enough to explain it again, right? So I have already explained how it is going to process one string which it is going to accept, and another string which it is going to reject. So if you find it difficult, please revisit the slides. I think the concepts will be much more clearer. Fine. And this much for today. In the next class, we will just see how we have seen the transition table. Now in the next class, we will see how to use transition diagram to represent the working principle of Turing machine. Thank you.